Every refinery, every power plant, every chemical site runs on heat exchangers, thousands of tubes quietly moving energy. This is how they work, and how we keep them healthy. A heat exchanger has one job: move heat from one fluid to another, without letting them mix. That simple function recovers energy that would otherwise be wasted, controls process temperatures, and protects machinery from overheating. When a bundle is pulled during a turnaround, you're looking at thousands of tubes, and every one of them is a pressure boundary. The most common design is the shell and tube. One fluid flows inside the tubes, the tube side. The other flows around them, inside the shell side. Heat crosses the tube wall, the fluids never touch. Baffles do double duty. They force the shell side fluid into a zigzag path for better heat transfer, and they support the tubes. Counterflow arrangement, hot one way, cold the other, gives the best temperature driving force. And notice, everything depends on that thin tube wall staying sound. Heat exchangers come in several families. Shell and tube, the refinery workhorse, handling high pressure and temperature. Plate exchangers, compact and efficient, limited by their gaskets. Air-cooled fin fans, no cooling water needed. And double-pipe hairpins for small duties. And within shell and tube, there is a whole engineering language, the TEMA standard, which we decode next. Shell and tube exchangers are specified by a 3-letter TEMA code: stationary head, shell, rear head. The middle letter, the shell, sets the shell side flow path. E, 1 pass, in one end and out the other. F, 2 pass, with a longitudinal baffle. G, split flow, in at the center, out at both ends. H, double split flow. J, divided flow. K, the kettle, an enlarged shell for boiling, the classic reboiler. And X, cross flow, where the shell fluid sweeps straight across the whole bundle. The first letter is the stationary head: A, a channel with removable cover; B, a bonnet; C, channel integral with the tube sheet; N, integral with removable cover; and D, special high-pressure closures. The third letter is the rear head: L, M, and N are fixed tube sheet designs, simple and cheap; P, outside packed floating head; S, floating head with a backing device; T, pull-through floating head; U, the U-tube bundle; and W, externally sealed. Combine them for the classics: BEM, the fixed tube sheet workhorse; AES and AEP, floating heads that absorb thermal expansion; AKT, the kettle reboiler; CFU, the U-tube; and AJW, for low pressure. Zoom into the tube sheet and you see the real story: hundreds of expanded tube ends, each rolled and sealed into the plate. The tube walls are thin, 1 to 3 millimeters, because thin walls transfer heat best. But that also makes them the weak point. A single failed tube means fluids mix, contamination, corrosion downstream, unplanned shutdown. And the service environment attacks those walls relentlessly. Fouling and scaling choke the flow and insulate the wall, killing heat transfer. Erosion and impingement where the inlet ends. General corrosion thins the wall evenly. Pitting makes pinholes. Stress corrosion cracking splits tubes along their length. And vibration at the baffle plates wears tubes from the outside. Every one of these mechanisms reduces the wall, and every one can be measured before it leaks. That's where tube inspection comes in. 5 techniques dominate: ECT for non-ferromagnetic tubes, RFT for carbon steel, NFT, the fin fan specialist, MFL for floors and tubes, and IRIS, rotating ultrasonic, for direct thickness measurement. You choose by material, and by the defect you are hunting. Eddy current testing first. A bobbin probe with an AC coil is pushed through the tube. The alternating current induces eddy currents, small circular currents, in the tube wall, flowing in loops concentric with the coil. When the wall is sound, those loops are symmetric and stable. But a pit, a crack, or a thin zone diverts that current, and the coil's impedance changes. Watch the impedance plane on the right. As the probe travels, the dot follows the liftoff curve. When it crosses a defect, the trace swings into a loop. The amplitude tells you severity, the phase angle tells you depth. ECT is fast, meters per second, and exquisitely sensitive on stainless steel, copper nickel, titanium, and brass tubes. In the field, the crew works through the tube sheet one tube at a time, recording a permanent trace for every tube. ECT detects pitting, wall loss, cracks, and baffle wear, and with calibration, it sizes the remaining wall. But there's a hard limit: ferromagnetic material destroys the eddy current pattern. Carbon steel tubes need a different physics. For carbon steel, remote field testing. RFT uses a low-frequency exciter coil and a detector coil placed far away, in the remote zone, 2 to 3 tube diameters downstream. The field from the exciter crosses the tube wall, travels along the outside of the tube, and crosses back in at the detector, a through transmission path, crossing the wall twice. Metal loss anywhere along that path changes the amplitude and phase the detector sees. The beauty of RFT: it's equally sensitive to inside and outside damage. It measures general wall loss quantitatively, and it works exactly where ECT cannot, in ferromagnetic tubing. Near-field testing, the fin fan specialist. Air cooler tubes are carbon steel with external fins, and the corrosion that matters hides on the inside surface, beneath the fins. NFT puts a driver coil and a pickup coil close together, so the field stays in the near zone, concentrated directly under the coils. That tight, intense field is sensitive to inside pitting even in ferromagnetic steel, at nearly the speed of ECT. When your fin fan tubes start losing wall, NFT is the tool. Magnetic flux leakage next. A yoke magnetizes the steel strongly, and magnetic flux flows through the wall, held inside the metal. At a pit or a thinned area, the metal can't carry that flux, so it bulges out and leaks above the surface. Hall effect sensors riding between the poles detect that leakage and map it to the defect's location and size. MFL is the worldwide standard for tank floor scanning, and a fast screening tool for ferromagnetic tubes and piping. And then there is the ultrasonic referee, IRIS, the internal rotary inspection system. The tube is flooded, and a probe carrying an ultrasonic transducer is pushed through. The water spins a tiny turbine, which rotates a 45-degree mirror, sweeping the sound beam around the full circumference. The pulse travels along the tube, the mirror turns it 90 degrees into the wall, and the echoes return, one from the inside surface, one from the outside. The time between them is the true wall thickness, direct, absolute, on any material. The price: tubes must be clean and flooded, and it is slow. But when you need the truth about remaining wall, IRIS is the referee. So how do you choose? ECT, non-ferromagnetic tubes, superb on pits and cracks, very fast. RFT, carbon steel, quantitative wall loss, inside and outside equally. NFT, fin fan carbon steel, inside corrosion under the fins. MFL, rapid scanning of floors and ferromagnetic tubes. And IRIS, any material, slow, but a direct wall thickness measurement. The material decides first, the defect type refines it. In practice, inspection is a system. Review the history and previous reports. Clean the tubes, dirty tubes ruin data. Select the method by tube material. Run the probes or the scanner. Analyze the signals against calibration references. Then decide, tube by tube, keep in service, plug, or schedule retubing. And report, because this run becomes the baseline for the next one. The takeaways. Thin tubes are the pressure boundary, and TEMA codes define the build. Match the NDT to the material, ECT for non-ferromagnetic, RFT, NFT, or MFL for carbon steel, and IRIS when you need the absolute number. Trend every run. Thanks for watching.